Dear participants, so welcome again. So the session will be starting at around 6:10 to 6:15. Okay. So let's stay connected. Thank you all. Good evening,
Hello.
sir.
Good evening.
Good evening, sir. Dr. Mukesh, sir. Good evening, sir. Sir, am I audible, sir?
Yes.
Sir, you are audible, sir.
Okay.
Okay, sir. With your permission, can we start, sir?
Yes, yes.
Okay, thank you, sir. So, a very pleasant evening to all distinguished speakers, respected faculty members, and enthusiastic participants. So, we, on behalf of the organizing team, on behalf of Vishnu Institute of Technology, Bhimavaram, delighted to welcome you all to day 5 of our 1-week online Atal FDP program on emerging trends and future prospects in advanced energy conversion technologies and applications. As we move toward the final stage of this FDP, I must thank all participants for their consistent enthusiasm and engagement throughout the sessions. Over the past 4 days, we have explored diverse areas from electric vehicles, SRM drives, PMUs, microgrid, solar PV systems, to energy policy and renewable energy integration. So, gaining deep insights from our esteemed speakers from IITs, NITs, CEA, and ORF America. So, today's sessions promise to be equally enriching, featuring two eminent experts who will take us through advanced concepts in power electronics and microgrid and government initiatives in energy conversion technologies. So, with this regard, we are honored to once again to have Professor Dr. Mukesh Kumar Pathak sir with us this evening. So, Dr. Pathak is a distinguished academician with more than 25 years of teaching and research experience in power electronics, renewable energy systems, and electric vehicle technologies. In today's session on the power electronics to microgrid, he will discuss the global shift towards the clean energy and integration too of wind power into EV infrastructure. So, with this regard, let us warmly welcome Dr. Mukesh Kumar Pathak sir to lead this fascinating session. So, thank you very much for again accepting our invitation, sir. We again welcome you to our FDP, sir.
Okay, so I'll start with some power electronics topologies today. I'll
Okay,
discuss
sir.
those.
Okay, sir. Okay, sir.
I'm sharing my presentation.
Okay, sir.
Okay, can you see
Yes,
my
sir. Visible, sir.
screen? Okay.
Yes, sir. Thank you, sir.
So now, in the power electronics applications, we are moving towards, we are creating a system which are capable of handling large amount of power, yet, operating at very high efficiency. So the requirements are high efficiency, and because you have a system where power flow is not unidirectional, because some of the converters will have to handle the bidirectional power flow, for example, charging or battery energy storage system. So high efficiency and bidirectional power flow is one of the features. And for this, for such systems, the topologies which are the recent topology which has invited the attention of many researchers, and in fact this topology has also become available in the market. So it is dual active bridge converter, DAB. This is capable of both DC-DC operation and AC-AC operation. And this converter comes with by default it comes with some kind of transformer. So the leakage inductance of transformer is used to operate this converter, and the operation is so devised, so planned, that it is used, this inductance is used to control the power flow and also create what is known as soft switching. Now we are moving towards a system where the converter efficiency should be increased to a limit. For example, the converter that we were using earlier, few years back or 10, 20 years back, there, the power handling capabilities were only IGBTs were being used, and power handling capabilities were few hundred kilowatt or few kilowatt, and the efficiencies of 90%, if it's 10 kilowatt, efficiency of 90% is, not is not posing any challenge, because 10% of power loss means 10 kilowatt, you lose 1 kilowatt. So handling, this dissipation of this power as such is not a big problem. And efficiency wise also, you are only losing 1 kilowatt. But suppose the converter rating is now, because of the renewable energy penetration, the converter requirements is now to handle powers in hundreds of kilowatt and even megawatt. So if the power rating is 500 kilowatt and efficiency is 90%, that means 50 kilowatt is the loss. And this 50 kilowatt power, loss of 50 kilowatt, as far as power is concerned, is a huge loss. And whatever kind of system you have, if the loss of 50 kilowatt is taking place on a continuous basis, it is something which should be we should be worried about. The second point is, any converter or any system which is creating a loss of 50 kilowatt, that loss dissipation itself will become a problem. So the power electronic systems are now looking at things like bidirectional power flow and efficiency enhancement. Now, apart from the device losses or device characteristics, how do we reduce the losses? And that reduction in losses can further be carried out by using soft switching. That is, using high frequency switching. That the losses will increase when the switching frequency is further increased. So the only way out to overcome this problem of very high switching losses is by using soft switching. That is, when you turn on the device, preferably, because this soft switching is in the modern devices, SiC devices, soft switching generally implies for turn on, because turn off loss, we have already seen that SiC device, turn off loss itself is very less as compared to conventional SI device. That means during the turn on of the device, we should somehow manage 0 voltage turn on, so that the power loss during turn on is reduced to 0. And if it is a DC-DC or even if it's AC-DC, it should be capable of operating or delivering power from low voltage to high voltage and vice versa. And symmetrical structure is something which brings advantage of modularity. You can use you can imply you can keep modules as spare, so that the spare cost and the reliability of system is increased. So first of all, we'll discuss this DC-DC converter using dual active bridge DAB topology. Now, dual active bridge appears like this. There is this is a single phase bridge on the primary side. So is the secondary side. So the structure of this bridge, this converter is symmetrical. Primary side also you have conventionally, whatever you had in a inverter kind of thing. You have 4 switches for single phase, and you have 4 switches here also. And the output points, these 2 are the output points, and so are these 2 points. So this structure looks very much like a inverter. If you have a DC supply here, the output is AC, and but the difference is now this converter and this secondary side and primary side. This is primary side full bridge and this is secondary side full bridge. Now the power can flow from primary to secondary and also secondary to primary. And the basic concept is lies not in the hardware but lies in the operation of this. So the converter operation here on the primary side and secondary side is controlled by what is known as modulation. How do we modulate the devices on the primary side and how do we modulate devices on the secondary side? That will determine the amount of power which flows from primary to secondary or secondary to primary. So what you can do is you can simply by modulation of these devices, you can control the power flow, amount of power flow, and you can also control the direction of power. So for example, simplest method of this is single SPS modulation and single pulse, single phase shift modulation and the dual phase shift modulation. So we'll see what are those. The primary thing is that you create a voltage here and here which are phase shifted. So the phase shifting is, this is the phase shift and this is the voltage on the primary side and this is the voltage on the secondary side. So if you want to deliver the power to secondary side, this primary voltage should be leading, and this angle of lead will determine how much power is fed to the secondary side. So by controlling this angle, we can control the power. And these are the this is the switching scheme, and this is the primary voltage, red lines, and this the other one is the secondary voltage. You can see the primary voltage is leading the secondary voltage, and the subsequent currents that flows line current would be on the primary side. This would be the current. So we have developed this kind of system for a DC-DC operation, and this will be useful in battery charging because the input is battery, EV charging. Input is DC, output is also DC. And if you from battery to vehicle or vehicle to battery, if you want to control the power flow, you can easily do it through this converter. And the transformer here not only provides isolation, but it also gives us an opportunity to enhance or reduce the voltage ratio. So if you are increasing the voltage from this side to this side, you can do it by duty ratio as well as by transformation ratio. So these are the specification. It is the leakage inductors which need to be designed specifically. Turn ratio we have taken 2.1 to ratio 1, and input side is 400, output side is 200. So it is typically a buck operation from input to output, and the reverse side it would be boost operation. And switching frequency is 550 kilohertz, and the power rating is 5 kilowatt. So this is a small system, even though it is sending a large power. The waveforms, these are results of the waveform. You can see this is one voltage, primary, secondary, and the current. So you can always say, you can compare it with the previous one, and there you can see that these are the waveforms, and this is the current waveform. Here in the experiment also, we can see the similar type of waveform. So the voltage between A, B, and CD are the transformer primary and secondary voltages, and ILK is the primary current of the transformer. This is the primary current. Now, the modulation of this converter, the important thing about this converter is, even though it appears very promising system, but there are problems. We need to fix those problems before this converter can handle large power and can also operate at high efficiency. So the important thing is what is the ZBS range. Now this converter, if it is operated in SPS mode, it has limited uh, zero voltage switching range. So ZBS is affected by load. If the loading is, if it is no load, you move towards non-ZBS operation. It is also affected by the voltage variation on the input side. And subsequently, this operation with this kind of operation, if you see the waveforms here, the problem is that the current itself is not, it's not symmetrical, or it's not a known, it's very unusual kind of waveform. And this unusual kind of waveform leads to very high peak current. So the problem is ZBS and higher peak current. And higher peak current leads to more conductive loss and loss in transformer winding also. So the modulation technique that we should aim at is one which can give wider ZBS, reduce peak current, and the transition from one mode to another should be seamless. And the other problem with this is backflow power. You can see, if you see the here, this is the region where the power would be negative. This is the region where power. So this dual active bridge has got a issue of backflow power, which is not contributing in power flow. So how to control that? That is also an important issue. So we look at these issues and see how the this modulation can be changed to do that. So typical modulation schemes are SPS. This is, SPS is single pulse modulation scheme, and this is, dual extended pulse modulation scheme, and DPS is dual pulse. So now if you compare these schemes, the SPS has got one variable only, EPS and DPS has got two variables. So we create another variable in these two schemes to control the power flow and operation, operation of the converter. So the complexity is, this is more complex. These two become more complex as compared to the first one, but we get extended ZBS range in these two. And using these two schemes, DPS and EPS, we can control the back power flow, we can reduce it, and we can also reduce the current stress on the switches because peak current would be reduced. And you can, the ZBS and operation and the current stress would be reduced over wide power range in these two. So overall impact is higher efficiency in EPS and DPS. So apart from that, these two, the resistive schemes, also see, now I'll discuss about seamless control, say seamless dual mode control of this DAB. In this mode, the modulation scheme is slightly, modified. So two variables are used to develop the control strategy, and control implementation is becomes, simpler. Two operating modes are used to achieve ZBS operation and low current stress during operation. Mode transition between two operating mode is seamless. You don't need to switch it off to transit this. And the junction capacitance of switch and magnetizing inductance of transformer are considered to develop the control strategy. So it is dependent on what type of transformer leakage inductance that you have and what type of devices you have with the junction capacitance. So two operating modes are mode 1 and mode 2. In mode 1, the primary and secondary voltages are quasi square wave waveforms. and two variables are sigma and d. Now you can see we are introducing the pulse width as another variable, and sigma is the shift. So two variables, the what is the uh, this voltage waveform width, and what is the shift. So that gives us another control, and the currents would be so controlled that the peak current is reduced. So with this kind of proposed system, what we have achieved is, you can see the EPS, then PS and DPS, all of them. This is the proposed one. In the proposed one, what we get is the reduction in peak current all over the range. So this is power range from 0.2 to 1 per unit, and this is the peak current. So peak current is reduced, all of is reduced as compared to others over the complete range. And you can also see this is for conversion ratio of 0.4 primary to secondary, similarly for other. So you can see some in one case it is the advantage is more. The second case advantage is not that high, but it is still the advantage even if the ratio is high. So this was the experimental prototype, and these are the experimental results showing the control of voltage, and the current now you can see is more or less smooth. It's not as having that much of peak as in the previous cases. This is for A is for K is equal to 0.4, power is 0.25, and second case it is 0.6. So the higher power mode. And then you can see ZVS waveforms also. You can see when the transition is taking place, the voltage is getting, it is reducing to 0. So this shows the transition, and during this switching, the voltage is getting reduced to 0, and that will ensure that when you turn on the device, the voltage is 0, and this will make the turn down loss 0. Similarly for other cases also. Different, we can see wide range of this thing, 0.25 per unit, 0.6 per unit, you have ZVS operation. Now, we can also use the same type of system, DAV, now for AC to AC conversion. Now, it is the AC input on this side, and the output is also AC here. But the difference now is, instead of using 4 switches, now we are using a pair of switch in every leg. Instead of one switch here, we have pair of switches. Similarly, pair of switches here. The purpose is to have bidirectional control operation. So if you see the first switch, this is same as the previous case, but the other second switch is now connected in opposite direction. So this switch will be capable of carrying controlled bidirectional current. So suitable for application with size and weight control constraints, only one stage of power conversion. And this capacitor is a AC capacitor, small capacitor, no electrolytic capacitor is required, and it has got a bidirectional power flow. You can use this to deliver power to this side, output side, or from output to input side. And it has got a soft switching capability, that is, the switches operate under ZVS condition. So the working is, this is the 50 Hz AC supplied to the primary side, DAV, which consists of bidirectional switches. The output of primary side bridges high frequency. Now, through modulation of these switches, we create high frequency AC, which is fed to the primary side of transformer. The transformer output, because this is a simple transformer action, so output is applied to secondary H bridge, which converts it back to 50 Hz frequency. through modulation of these switches. So the waveforms would be, this is the input voltage waveform, this is the input current, and this is the output voltage 50 Hz, but different value of voltage, and this is the output current. And in the transformer, this is the primary side waveform, which is an envelope high frequency pulse waveforms with an envelope of 50 Hz. So would be the current. And similarly, secondary side also high frequency envelope with the high frequency pulse waveform with 50 Hz. The other possibility is now the similar kind of thing. If you wish to obtain AC input, AC output, instead of using DAB, LLC-based single-stage converter can also be used. Here, this simplicity is that on the input side, there are two bidirectional switches, but it is a half-bridge kind of system. There is no, here there are only these capacitors, and this is transformer. And the output side, you have a rectification followed by inverter. So if you compare this with the previous one, then you have, if you see the previous one, this one, there are how many? 2 to 4, and then 4 here, 8 switches, and then 16 switches. Whereas in this case, we have only 2 to 4 and 4 switches here. So only 8 switches. As compared to previous case, this is, the number of switches is reduced to half. And again, because of this switching modulation of operation of these switches, you create a high frequency envelope of AC voltage on the input side. So would be the output side. Only, transformation will take place. And then this diode would be used to rectify this. And then the output would be, this rectified output will be applied to this inverter, and this inverter will be synchronized with the operation will be synchronized with respect to this waveform, and you get a 50 Hz output. So in the process, what you can do is you can use this transformation ratio to reduce or increase the voltage. So you can use this as a step up or step down system, generally step down. So this kind of LLC system has got a, salient features of this are, it's a single stage conversion directly from AC to AC. Number of switches is reduced, and it eliminates the folding bridge to connect AC side grid. So input side, you do not have full bridge, and there's no bulky capacitor, reduced hardware requirement. ZPS operation is over wide range because you are synchronizing everything with the 50 Hz to that thing. So reduce switching loss. Okay, so these are the different operating modes. How, when this supply is positive half cycle, how will it operate? Then the negative half cycle and different currents in the output, positive and negative. And okay, let us leave this. This is the prototype, 2 kilowatt. It operates at 25 kilohertz, and the capacitor is only 5 microfarad on the AC side. As inductance is required, filter inductance is required, and then the capacitors. And the transformer is designed with leakage inductance of 148 microhenry. These are the experimental waveforms. You can see these waveforms as we discussed earlier. And this is the high frequency. This is the input voltage waveform and the output waveform. These are the high frequency transformer primary and secondary waveforms, magnified views, and finally the output current and output voltage. Similarly, what we can do is we can have this bridge is the same, the input side is same, but the output side now, we can, instead of having, a rectification and then uh, inverter, we can use that functionality can be, integrated into one thing. So this becomes single stage semi-active bridge based SST. So the topology this uses a semi-active bridge on the secondary side also, and it eliminates the reverse power flow problem, and also minimizes the secondary circulating current, and achieves the power flow capability controllability using secondary phase shift control. So the waveforms would be input side is 50 Hertz, and on the transformer input you will have a this uh, uh, pulses which with an envelope of 50 Hertz, and this would be the transformer current. And similarly, the output side waveforms also will see during the experiment. These are the switching schemes, because you have, there are 4 switches on the primary side, and similarly, there are, switches on the secondary side also, 5, 6, and then you have, this R4, R3, R2, and R1. These are the operating modes. I think the details you can see yourself if you refer to the literature. It will have ZBS, and we'll see. We have found out as to how to operate it in ZBS. What should be the values of alpha and beta for ZBS operation, and how should we minimize the peak current. This is the hardware results. This side waveforms. This is input side voltage and the output side voltage. These are the magnified, voltage currents, and input voltage and output voltage in primary and secondary resonant currents. So you can see this shows that turn on is ZVS type, and this also shows, so secondary side is ZVS, primary side is also ZVS. Similarly, you can now a DAB-based AC/AC system can also be built. That will have input side is a control rectifier, and then this is a half wave configuration, and then again, this is this would form a DAB, and then the output side is the output is DC. So if you compare it to the first topology, then we had DC input here, then this topology, this configuration, and the output side also this configuration, and DC here. So if we add inverter on the output side, it becomes AC, and since there was a DC here, now we can get that DC from AC, so there is a control rectifier here. So this is, DAB based, the first one that we discussed, DAB based, and with the capability of AC/AC. But you can see the number of switches, and it's again the question of number of switches. You can see 4 here, 4 plus 2, 4 switches plus 6 switches, then 4 here, so 10, and then 40. So we had another topology initially with 16 switches. So as compared to that, it is less, but still, the number of switches is large. These are the waveforms of operation that we can I can skip. What we have done is that we have designed a control of this so that the peak current is reduced. So the peak current is reduction. We'll see the basic purpose is to reduce the stress on the devices by means of reduction in peak current, because ZVS is there. But apart from that, what is the shape of current so that the devices are not stressed unnecessarily? So we have discussed, we have developed this, compared this EPS1, EPS2, and all those current optimization and things. This is the system operating at 25 kilohertz prototype, and this is the design of leak inductance for a transformer, and then the capacitor on the input side, inductance and rated power. These are the waveforms under different modes of operation and ZBS. So you can see ZBS, taking place here also. The voltage reduced before the turn on of the device in all cases. So in short, what we can do is what we can conclude is that the major challenge in all these converters is to operate the converter in a mode where the losses are minimized. And loss minimization will need efforts in operation of the converter in ZBS mode. So now, the last topology that I'll discuss is bidirectional half-bridge AC-AC converter topology. Now, this is a topology which is capable of bidirectional operation. So half-bridge, primary and secondary with bidirectional, both of them are half-bridge, but because of two switches, here and two switches there, it is capable of bidirectional operation. So primary side half-bridge generates high-frequency AC voltages, which are applied to the transformer. So solid-state transformer, high-frequency transformer is sorry, not solid-state, but high-frequency transformer is there. And this converter will generate high-frequency AC input to the primary of the transformer. Secondary side half-bridge generates live. This will generate secondary side modulation is carried out in such a way that output is 50 Hertz. So from the high frequency output that gets connected to this half-bridge, we generate 50 Hertz output. So it offers low active device count, soft switching capability, and simple circuit configuration. So this configuration has got low switch count. You can see 4 switches here and 4 here, and complete conversion from AC to AC. 8 switches only. It is, ZBS range gets narrow for high voltage of conversion ratio. This is the main problem. If you compare its ZBS range with the power output, this range is shrinking because that this dotted line show that this ZBS is not there. So as you increase the power range, the ZBS range will decrease, and particularly low low power operation, the ZBS will not be there. So at low load condition, ZBS is lost. So we can, find out the ZBS condition for this by using these equations and understanding it from the waveforms. These are the simulation results of input and output waveforms. And this is the current in the transformer, primary. Similarly, we can further get into this. This is a hybrid half-bridge AC-AC converter. So here, we have 2 switches. So it is bidirectional path flow capability, bidirectional operation. But on the primary side, we have diode rectifier and then this converter primary half-bridge. So this has got a low active device count. On total devices are 6 only, but requires large electrolytic capacitors. Are eliminated. High power density and reliability, and bidirectional switch-based half-bridge circuit at the output side. This is a prototype of this type of configuration, operating at input voltage of 100 volt, 25 kilohertz switching frequency, And these are the transformer parameters, and the power rating is 800 watt. This is the input voltage, this is the output voltage waveforms, input output, and the power. So with this, I'll take now a leave of you. If you have questions, you can ask. About the configuration that we have discussed, or any other question that you have.
Thank you, sir. Thank you very much. So, dear participants, if you have any questions, please interact with sir. So we expect participants to please ask questions if you have any. Sir, I have a question, sir.
Yes, please.
Sir, first of all, thank you very much, sir. You have shown the many power electronics topologies with along with the circuitry and simulations and hardware setups and hardware results. It was a nice experience. Sir, is there any specific topologies which are with respect to bidirectional flow for EV applications, which are using a real-time application, sir?
DAB is the one which dual active bridge.
Okay, sir.
Is the one which has got an inherent capability of bidirectional operation. Else, if you design any other topology, because DAB, the power flow is controlled by phase shift between primary and secondary voltages.
Okay,
so
sir.
That is the simplest way of doing it. But the DAB, the problem is power rating. Whereas you go to very high power rating, these DAB topologies have a problem of ZVS operation. Because if you don't have ZVS operation, high power rating, the losses will increase very large.
Okay, sir.
Otherwise, if you want to operate in bidirectional power flow, then you have to have more devices in the same circuit. If you have half bridge, you have to have, instead of 4, 8 devices.
So
And the
we'll be
modulation
connecting
scheme is the heart of this.
Okay, sir.
Yes.
No, sir. Please continue, sir. Means that's what you said, no, sir. Means we'll be connecting in cascade for bidirectional flow.
2 devices instead of 1 device. One in they are in series but in opposite direction.
Okay, sir. Okay, sir. Sir, sir, we'll be seeing chat box, sir. Someone posted here. Sir, which converter most suitable for electric vehicle without EMI? Is the question, sir.
See, EMI issue is not that much problematic these days, because once you are going for a ZVS operation, the EMI problems are automatically solved. If you have, when you have ZVS operation, because EMI is created when you have a switching at high frequency. But if high frequency switching is without high voltage and high current, EMI is automatically reduced. So most of the topologies these days for EVs, they come with inherent or inbuilt ZVS operation. And these are very high frequencies. So EMI problem, if you do not use ZVS operations, then EMI problem will be magnified. But because we are operating these converters in zero voltage switching mode, the EMI problem is much reduced as compared to conventional high frequency converters.
Okay, sir. Okay, sir.
So you don't require special EMI filters. The filters that we use in conventional, in low power converters, that can be used, because some some small amount of EMI. If you want to protect against this, you can use those small filters.
Sir, one more question from our side, sir. Sir, is there any scope of the application of machine learning in power converter topologies, sir? Means for research purpose.
Now you can use them for optimization only. For example, in DAB and all those converters, when you are finding out these operations taking place, dynamic operation, two control variables. One is the load, or two variables. One is the load, the second is the output voltage. Under certain loading conditions and certain output voltages, there are chances that ZVS is lost if you do not use values of phase shift
Optimal values.
and values of this pulse width. If you do not use proper values of them, then these two parameters can cause loss of ZVS. So you can use this for training the converter system control to operate within the ZVS range.
Okay, sir. Okay, sir. Thank you, sir. Sir, we'll see one more question is there in the chat box. Is there any new semiconductor devices recently introduced in order to eliminate switching and conduction losses, sir? This is a question.
See, we have been using IGBTs for a long time. Now, SiC devices have come. SiCs, silicon carbide devices, because IGBT, conventional IGBT is silicon device. And again, gallium nitride devices also come. These are the devices which can operate at very high frequency with low switching loss. But again, the frequencies are targeted in these devices so high that even though the losses are reduced as compared to conventional SI devices, but with such a high frequency, the losses will become high due to both increase in the power rating and increase in the switching frequency. And to take care of this, we have to develop topologies where the operation is under ZVS control ZVS. So two type of devices are GaN devices. GaN devices are used for low power rating and high power rating SiC devices. These are the new devices which are now they are. I think they have not become as popular as IGBT, but they are gaining popularity.
Sir, one more question, sir, in the chat box. Can we design simple converter with less components instead of complicated designs?
No, it all depends on what is your target, what type of output what type of system you are looking at. How can you see if it is oversimplified, functionally it will not be capable of doing so many functions. So when you want the converter to carry out so many functions, you have to have some complication, and then you start from most complicated one, then try to reduce the complication. And this is what the research about topology is, to reduce the complications.
So thank you, sir. So participants, if you have any, it's a final call. If you have any questions, please ask. So if you don't have any questions, we'll be closing the session. Sir, with your permission, we'll be closing the session, sir.
Okay, thank you.
Thank you, sir.
Thank you, sir. Thank you so much, sir, for your yet another enlightening session. For your comprehensive discussion on the synergy between the powertronic topologies and the electric vehicle sections has truly expanded our perspective on renewable and EV mobility and hybrid energy systems. So thank you very much, sir, for sharing your valuable thoughts. Dear participants, we'll be moving to the next session, which is led by Shri K. Satish Kumar sir. Yesterday we have a session with the resource person. So this session will be starting at 7:30 p.m. So all the participants are requested to join at 7:30 p.m.
Okay, sir.
Let's stay connected. So we'll be trying to reach the resource person as early as possible. Thank you. Good evening, sir. Sir, am I audible, sir?
Yes, sir. Good evening. Very good evening.
Thank you, sir. Welcome back again, sir.
Yeah,
So,
thank you.
dear participants, we now move to our second session of today's evening, which is led by Shri K. Satish Kumar, sir, Deputy Director, Central Electricity Authority, New Delhi, a highly experienced professional specializing in grid operation, system monitoring, and renewable integration. With more than a decade of expertise in the national grid domain, Shri K. Satish Kumar sir has worked extensively on real-time system supervision, fault analysis, and smart grid solutions for renewable networks. So, in today's lecture on government initiatives in energy conversion systems, so he'll be highlighting the modern diagnostic techniques and the performance analysis methods for the application of intelligent monitoring systems. So, with this regard, please join me in welcoming Sri K. Satish Kumar Garu to the virtual platform. Thank you very much, sir, for joining us. So,
Yes.
over
Thank
to you, sir.
Yeah.
Thank you, sir.
Yeah. Is it visible, sir?
Yes, yes, sir. Visible, sir.
Yeah. Yeah. Good evening, one and all. Now we are going to discuss on the topic of government initiatives in energy conservation. There is a one famous quote by Mahatma Gandhi, the father of nation. The earth provides enough to satisfy every man's need, but not every man's greed. So he emphasizes on energy conservation in this with this quote. We have this earth provides enough resources which is satisfy the needs of the man but not man's greed. So before going to the topic, let us discuss the importance of this energy conservation. Many of you know that we use energy faster than it can be produced. Coal, oil, and natural gases takes thousands of years for formation, but we consume this in months and years. And we have limited energy resources, but India has a most populous country, so there is really a need for energy conservation. And based on the data from sources like Energy Institute and Worldometer, using 2024 data analytics, they came to a conclusion. Our oil resources in the world are last for approximately 47 to 56 years if you consume the same rate as we are now consuming. If you continue the same rate, the consumption rate, it will last in 47 to 56 years. Similarly, natural gas, if you consume in the same rate at which we are consuming the same rate at which we are consuming now, it will last in 49 to 53 years. And coal, it will last in 114 to 140 139 years. So this indicates we have a really limited resources of oil, natural gas, and coal. So there is a concept of energy conservation is really important because of we have limited resources, limited natural resources. And you know this, we are dependent country in terms of crude oil. We import 85% of the crude oil from the other countries, which costs around 8 lakhs crores annually. And there is a famous says that energy saved is energy generated. If you save 1 unit of energy, it is equivalent of 2 units energy produced. You may ask me, sir, what is this? If you save 1 unit of energy, how it is equivalent to 2 units of energy produced? As you know, the ATC losses, distribution losses, technical losses, commercial losses, nothing but some people will not pay the billing, so they will rationalize that they will adjust to the energy accounting. So this technical losses, commercial losses, and transmission, distribution, all these assets if you include, which is if you take consider approximately 50% all this is efficiency of the system, then it will comes to a 1 by 0.5 efficiency, it will becomes 2 units. So if you save 1 unit, it is actually you're saving 2 units of energy produced. So we'll go some brief background what government really want to do in this energy efficiency. As I told, the importance of energy conservation, government also emphasized and given importance for this energy conservation from 2000 onwards. They understood such a populous country, we need to bring certain institutional framework to save this for this energy conservation. So in 2001, they passed the Energy Conservation Act, EC Act, popularly called EC Act, Energy Conservation Act in 2001. And that in that bill, they proposed a institution called Bureau of Energy Efficiency, BEE, which is a nodal statutory body. Statutory body means by Parliament Act, if they established a body, so it is called statutory body. Constitutional body means which is there in the constitution itself, like election commission and union public service commission. So 2001 they brought this energy conservation act 2001, and they established this bureau of energy efficiency to implement this energy conservation act. The main the core of its energy conservation is reducing unnecessary energy usage by promoting efficient practices and technologies. So this institution works, this Bureau of Energy and Efficiency works mainly on bringing this latest technologies, efficient practices, so that we can save the energy. And as you know, now the energy demanding is increasing day by day. Like in 2006 and 2007, if you see our annual energy consumption in terms of billion unit, it is around 6 lakh units. But now it is comes to be around 16 lakhs units of energy consumption is there in the every year. So you can see how much it is rising at 6-7% of minimum. At 6-7% rate minimum, this 6-7% the energy growth is going on. So we need this so there is really a need for energy conservation. So government focused on this in 2000 itself, early in 2000, and they brought this act in 2001. And in 2002 March 1st, this statutory body under Minister of Power, Bureau of Energy Efficiency, they established. And the primary mission of this Bureau of Energy Efficiency is to develop policies and strategies to reduce the energy intensity. Energy intensity is nothing but how much energy is used to produce a unit of economic output. In generally, 1 unit of economic output, nothing but GDP, such as 1 unit of GDP. So energy intensity, if it is lower energy intensity indicates a more efficient system. To produce same unit of output GDP, how much energy you are using. If you use lower energy to produce the same output, that is really a more efficient system. So India wants a more efficient, energy efficient economy, then only it will be sustainable, because we are such a populous country. We need to use this energy conservation methods, so that our energy requirement reduces, thereby we can save in dollars and rupees. Now we'll come to this institution, basic function and initiative of BE, Bureau of Energy Efficiency. Their major, these are the major functions, I can say. Standards and labelings. Many of you have seen in that 1 to 5 star rating on your applications, air conditioner and refrigerator. So this institute mandates this star labeling, that the more stars is more energy. You might have seen in your refrigerators and air conditioners, the more stars, the more efficient. I will discuss in detail in the next slides. These are just a glimpse of the functions of BE. And BE implements this perform and achieve and trade. It is a market-based mechanism to reduce energy consumption, especially large industries like aluminum and cement. These are very energy intensive industries. So government targeted this energy intensive industries to reduce the energy consumption. Next, they also introduced in 2017 Energy Conservation Building Code. They brought a code called as a Energy Conservation Building Code 2017. So it mandates what is the minimum requirements for an energy efficient design of large commercial buildings. So like ventilation and what the ventilation and space, other I will detail explain in the next slide. So they brought certain codes. The code explains the minimum requirements that commercial building should have, so that energy efficient can be maintained. And there are some other programs they initiated, like assistance in deploying energy efficient technologies in industries and establishment. So they given financial support and technical support for this energy efficient technologies. And also they are conducting national awareness campaigns, conduct public programs, and some painting competition to school children, encourage energy conservation. And also they are doing this capacity building, because in India these are really we have a lack in capacity building.